Okay, so last time we basically, I think, if I hope I forgot. I was teaching just coming out from the airplane, and I used some piece of paper which I lost. And but I think I finished this discrepancy and the mixing lemma for biregular graphs, right? That's basically what we did, and we did it till the very end. I think I did it not in the optimal formulation, so maybe today I will reformulate it again. And we started the simplicial complexes or not at all?
It was the first lecture.
What?
It was the first lecture, there was some words.
Yeah, first lesson in the introduction, no, but last time, so okay, good. So today we will start with simplicial complexes. Let me go over very quickly on the basic definition, and then what I'm aiming to is a kind of a mixing lemma for simplicial complexes. So today, for the first time, we start to go to the higher dimensional situation. So a simplicial complex is a family. I mean, I'm taking an abstract kind of definition, a family of subsets. X, we call it, of a set of, we'll call it vertices, V, and which will, in a minute, also X of 0 will, is a family of, say, finite subsets. Now, in principle, V can be infinite, but the sets we will talk about will be always finite, such that which is closed under inclusion i.e. if F1 is in X and F2 is a subset of F1, then F2 is also in X. And if let's put just a few names very quickly. If the size of F is equal to I plus 1, say that the dimension of F is I, and F is, sometimes we call it I face, sometimes we call it I simplex, sometimes we call it the I cell. All these names are used. So for I equals 0, these are vertices. For I equal 1. So I equal 1 means that set of 2 points, these are edges. I equal 2, we call it also triangles, etc. Right? You understand what we have in mind here. The dimension of X is the maximal or the supremum. I mean, it always will be maximal because we will talk only about finite dimension. In principle, one can talk about simplicial complexes of infinite dimension, namely that there is no upper bound, but that's not the supremum of the dimension of the faces F, where F is in the collection, and we usually will call X uniform if all maximal faces of X are of the same dimension, and because well, I mean, we always so now because every face is inside the maximum face, it really means that everyone is inside a face of dimension D, and we are really going to look at nice complexes. I mean, I think, of course, one can talk about pathological cases, but somehow the whole point of this course is to show some exotic phenomena, but in nice simplexes. And the maximal faces are sometimes called chambers. And codimension one faces sometimes called walls. And it's like you have chambers, and between the chambers you have walls, right? You have rooms and you have walls. The room is are the maximal faces. And the gallery, so I'm just putting words here, is a sequence of chambers, say C1, C2, up to Cn, such that for every I between 1 up to n minus 1, Ci intersection Ci plus 1 is a wall. So a gallery is something that you can walk from one room to another via a common wall, right? So it's clear what is a gallery.
I think uniform is sometimes also called pure.
What?
Pure.
Pure. Ah, okay, maybe.
I think both are used.
It's more common to.
No, both are used.
Ah, both. Okay. Pure. Okay. Let me just make the remark that in the literature, the literature sometimes depends what is your, if you come from more topological kind of pure mathematics orientation, you prefer to talk about simplicial complexes. If you come from an abstract combinatorics or computer science, people talk about hypergraphs, but basically the two notions are equivalent. So let's just an hypergraph, just to set language. Hypergraph is a collection of subsets we call edges. There they call edge to everything. It's mathematically the same thing, but it's two different cultures somehow. So you should be aware of both. An hypergraph, so graph is a set, and then we define what are edges. An edge is a set of two elements. And a graph is a subset of sets of two elements. Now, in hypergraph, you're allowed to take different subset of different size, not necessarily two. And in principle, you are allowed also to take of completely different sizes in a hypergraph. But usually the interesting are those such that you take triples, so you take D sets. So I think in hypergraph is called uniform or pure uniform, I think. Hypergraph, I don't know, H. So here we don't assume that it's closed under inclusions. That's the only difference. And somehow, for some reason, they call edges the sets. And it's a little bit confusing because if an edge there can be with three elements, they still call it an edge. And I think it's called H is uniform if all subsets, say it's a D uniform, if all subsets are of size D. And now this is also a little bit frustrating because in their language, D uniform means that it's in our situation is dimension D minus 1. So be careful about that. But the point is that there is basically a one-to-one correspondence between simplicial complex. For every simplicial complex, give you hypergraph.
Gives you a family.
What?
The skeleton gives you a family of hypergraphs, not one.
No, you can take, I'll tell you I'll define it in the following way. I mean, I take a simplicial complex and I define an hypergraph such that the hypergraph H contains all maximal cells of the simplicial complex. just the maximal ones. And I'll define them as the hypergraph. And given hypergraph H, I can define a simplicial complex by taking H and make it closed under inclusion. So well, it's okay. Formally speaking, it's not. It's maybe not one-to-one, but at least it's one-to-one between, let's say, between uniform. I think between uniform simplicial complex and uniform. Yeah, here it will be exactly one-to-one, because then they have all of them have the same size. Okay, you understand what I'm saying? It's trivial things. I mean, it's nothing of importance. I just want you to be aware, and sometimes it's more convenient to talk in this language. Sometimes, I don't know, for me it's always more convenient to talk about simplicial complexes. It looks like sometimes there is no point to talk about simplicial complex because we are really, even this overlapping property that I defined in the first class, I really care only about the maximal chambers there. That's the only thing I look. So it's, in some sense, it's natural there to think about the hypergraph structure and not about the simplicial complex structure. But as I said, this is not a real. Okay, that's just for words and languages. Here is something which is well, later on maybe will come up. The chamber. Just maybe let him out. A simplicial complex is completely, that's always, it's completely determined by its maximal faces, maximal simplexes. Yeah.
Why do you have to add the uniform to make it one-to-one?
What?
Why do you have to add the uniform?
Because in principle, if you take a simplicial complex, and then I'll give you two hyper edges, a hypergraph connected to them. One will be only with the maximal of him, and one which will be exactly equal to him. If you don't ask, if it's not uniform, then they both will give you the same. But you understand, it's not a real issue. Okay. Okay. Now I want to get to a notion which looks maybe a little bit artificial in the first side, but we'll see that that will be an important notion, and in some sense, it really enrich our world. And this is a coloring of simplicial complex, or maybe I prefer to call it a type. So let F, and the definition. I will work now, as I said, in all the, I think we always will talk about uniform, all our simplicial complexes will be nice. So let X be a uniform simplicial complex of dimension d, say. Assume there exists some function tau from the vertex. I forgot to put notation. The node, I'm going to put it right away here. The node xi is the set of faces of dimension I. So assume there is a function from x0, namely from the vertices to the set 0, 1 up to d plus 1.
To D.
What?
Up to D.
Up to 0, up to d. By the way, it doesn't have to be up to D. Sometimes it would be convenient to work with 1 up to D plus 1. I mean, I have an assignment to a finite set of colors. You can think of it as I'm coloring the vertices, such that for every chamber C, so what is chamber C? This is simplicial complex of dimension D, so a chamber means a subset of order D plus 1. For every chamber C, tau restricted to C is 1 to 1. So this is called, tau is called sometimes coloring or a type function. And if F is some face of dimension I, so F is a set, I don't know, Vi 0, V0 up to Vi, then the type of F will be simply the set tau of V0 up to tau of Vi, like the colors of it. And if I is a subset of the colors, 0 up to D, then Xi, I hope it won't confuse us, will be all faces F, such that the type of F is exactly this R. So that the colors we are using for them is and now let's give another definition. Which we kind of want to extend the notion of regular graph. We know that between graph theory, regular graphs are the nicest sum of graphs that think regularly. Now here, it seems to be in various examples that it's better to relate it to the coloring. Definition, a simplicial complex X with type function tau is called regular if for every two subsets I inside J inside the set of colors 0 up to D, there exists a number k depending on I, depending on J in N, such that every face F in Xi is contained in exactly K, I, J faces F prime in Xj. I know that this looks a little bit artificial, especially that I'm putting you with the color, so let me give you right away example and show a few examples, and you'll see that sometimes there are interesting simplicial complexes which are not regular if we don't put the coloring function, the type function, but they are regular once we put the type function. Okay, so let's see some important examples. starting example, these are the most important examples, so I'll take a little time to play with them. Example, let F be a field. In fact, I can take any field, not necessarily finite, for this example, but I prefer to work with finite fields and because eventually that's what we are interested. So I'm taking a field of order Q, and I will take, and let n be some number in n, and we'll define the S and Q as for spherical or the flag complex of subspaces of Fq to the n. So let's see what we mean by that, i.e. the vertices are all subspaces of Fq, all of Fq to the n, different but not than the full one and the zero. All proper one. Proper in both senses, not everything and not zero. I take only the subspaces between them. And we say that a subset W0, Wi, a set of I plus 1 subspaces form a cell, a face, if maybe after this is a set, so we can if maybe after reordering, right? I mean, there is no ordering at the moment between them. We have W0 inside W1, inside W2, inside W1. So this is called, in linear algebra, it's called a flag, something like that. It's called a flag of spaces, and all the flags are the simplices. Okay. Now this is clearly a simplicial complex, because to be a simplicial complex, it's not a big deal. You don't need anything except of being closed under inclusion, right? And of course, if you have a subset of a flag, is also a flag. So this is a simplicial complex. Now let's see what are the maximal. What are the maximal flags? It's clear that the maximal flag, whenever I have a flag, if it's not a complete one, I can put between them, if the quotient here, if this is always containing 0, and this is always inside Fq to the n. If the dimensions of the relative quotient here is more than 1, I can insert various subspaces inside there. So a maximal faces are exactly the so-called maximal flags, or complete flags. I don't know how it's called, which is W1 inside Wn minus 1 with the dimension of Wi exactly equal to i.e. of size n minus 1, right? Because we don't take neither 0 nor the full space. So the dimension of this is a little bit confusing. So remember that is n minus 2. Okay? The dimension of the flag simplicial complex of all subspaces of f q to the n is exactly n minus 2, and everyone is contained in this. And this is a uniform, right? And of course it's a uniform. Okay, now what is a type function here? I'll denote that tau of W to be the dimension of W. Well, now if you insist that the colors will be between 0 to the dimension minus 1, I should write the dimension minus 1. But it would be ridiculous, right? I mean, so here the type function is getting values between 1 to n minus 1, not between 0 to n minus 2. That's okay? I think it's more natural. I mean, we can. I define it as like it should get. In the example that will work later on, it will be between 0 and the dimension minus 1. And the dimension, right? We should get always one more than the dimension because we want to give, right? We want to give that the types, the number of colors is exactly the dimension plus 1, right? Because we want that every chamber, that tau will be 1 to 1 on every chamber, right? And the chamber contains d plus 1 points if d is the dimension. Okay, clear, right? It's okay? But here we have the number of colors is 1 up to n minus 1, while the dimension is n minus 2. And let me make the point. This is regular. Why this is regular? And why this is regular? Because you see, if I have I inside J, what does it mean? I have a subset of the number 1 up to n minus 1. And I have another one. And if I take a face of type I, say if I is say equal I1 up to IT, say, or I1 up to IT. So what does it mean if f is in xi? It means, here is the definition of regular. Let's keep it here and let's erase. So what we should prove? We should prove that if we have a larger set, then the number of faces of type I inside faces of type J depends only on I and J and not on the specific face. So what does it mean F in Xi? F in Xi is really a collection W I1 inside WI2, right, where inside WIT, where the dimension of WIJ is exactly IJ, and what is a face of type J is a flag which is a refinement, how do you say in English? Refinement, which is a refinement of this flag. Namely, I have more indexes in J, more dimension. So let's say this is dimension 1 and this is dimension 3, and 2 appears in J and do not appear in I. So in a flag of dimension, in a flag of type J containing this Y, I will have WI1. I have to put here something, and then I have to take WI2, etc., right? Are you all with me? The number of this something is completely irrelevant what is WI1 and what is WI2. It only depends on the difference between their dimensions. Right? If this is 1, if this is dimension 1 and this is dimension 3, so the quotient space here is of dimension 2, and I can put exactly q plus 1 subspaces, right? Because in a space of dimension 2, there are exactly q plus 1 subspaces of dimension 1. Right? Is it clear? And the same thing, and if the difference here is bigger, okay, doesn't matter. The number of subspaces that I can put in between them does not at all depend on what is this specific one, what is this specific one. It really depends only on the isomorphism type of the quotient of them. And the isomorphism type of the quotient of them depend on the set I, capital I, and not depend on what are these subspaces. Is this clear? I'll show you in a minute that without the type function, these simplicial complexes are not regular. So they're really playing a role because we really, and we are going to use this regularity of set. We are going to use this regularity. We are going to use this coloring regularity. So I hope this is clear. I mean, it's a simple linear algebra that it should be clear to everybody that this is regular. Let's take maybe let's do some computation with some examples, and then by the way, let me give you a nice exercise. Which, to be honest, I'm not sure what's the easy proof, but I want you to look for an easy proof because some of the way I'm thinking about it is a little bit complicated. I'm sure there is an elementary linear algebra. So let me give you a definition. A simplicial complex, a uniform, say simplicial complex, is called chamber complex if every two chambers can be connected by a gallery. And you understand exactly what I mean by that. Remember, we said a gallery means that we start with one chamber and we have a sequence of chambers ending with another chamber such that every two along the way intersect in a wall. Okay, they are connected by a gallery. And then the exercise here prove that S and Q is a chamber gallery, is a chamber complex. So we have to understand how we pass. So you see, what is the real content here? The real content is that whenever you have two flags, two complete flags in the vector space Fq to the n, you can move from one another by small changes. Small changes in a way that every flag and the immediate one are different by only one in one of the dimensions. But there is a little challenge there. I'm sure that, I don't remember, I probably saw a proof also by direct linear algebra. One can give sophisticated proof, and I kind of remember the sophisticated proof, but there should be proof, so this is a challenge. I think it will be good, and if somebody can do it, please either write it or come next time and present it on the blackboard. I think that would be good to understand. But okay, let's take now some example, and you will see right away that they give us very interesting combinatorics. So let's take there is no point to talk about dimension 1, because dimension 1 we get the empty set. So the empty set is an important set, but not just an interesting simplicial complex. So let's start with 2. We'll see that already with n equal 2 we are getting something which is an interesting. With what we expecting, right? With n equal, n equal 2 is not interesting, n equal 3. N equal 2, we are supposed to get simplicial complex of dimension n minus 2, which is 0. And indeed, here we get, for n equal to, S2 cube is just a set with no connection, right? Like only vertices. And how many, at least how many points there are? It's just a set of q plus 1 points. Because q plus 1, right, is the number of one-dimensional subspaces of fq squared. Right? But if you want, this is the projective line. But there is really no structure here somehow. There are no edges, there is nothing. It starts to be interesting with n equals 3. Here, let's see what we get. So what we have here, the vertices are all subspaces where of dimension 1 or 2, right? Not dimension 0 and not dimension 3. And a flag, what is a flag? A flag is if one subspace is inside the other. So we can think of them as here is the set of, this is the set of subspaces of dimension 1. Here is the set of subspaces of dimension 2. By the way, what's the number of them? How many subspaces we have of dimension 1? How we compute it? You know, you take the number of non-zero vectors. You have q cubed minus 1 non-zero vector, and you look at the subspaces spanned by them. They give you one-dimensional subspace. But every one-dimensional subspace is obtained this way q minus 1 times, because every non-zero vector in it gives you, so this is the number of dimension 1. At dimension 1, then this is the number of those dimension 1. What is the number of dimension 2? It's the same, right? Why? Duality, right? We don't have to do the work. By the duality between the dimensions, between dimension I and dimension n minus I in general. And there is a notation for that, such number, which is quite common. N over I cube is like the binomial coefficients, and in many ways they behave like binomial coefficients. N over I cube is the number of subspaces of dimension I in Fq to the n. And that's not so difficult to compute it, to write the formula for that. We'll do it in the next example. Here it's easy. Now, and then the flags here is if W here and W1 here and W2 here, so we put an edge if and only if W1 is inside W2. Right? Now this is, so we get a graph. We got a bipartite graph. This is a very famous bipartite graph, which is used a lot of combinatorics, because you remember, I mean, I hope you learn, I don't know if these days, do you learn some projective geometry somewhere? Somehow it's not anymore in the curriculum of linear algebra, and I think it's kind of forgotten. Everyone know what is projective geometry? Somebody doesn't know. Yeah? Everyone know? That you take a geometry like what is a projective plane? You take a three-dimensional vector space and you define the one-dimensional spaces as points, the two-dimensional spaces as lines. So, okay, you do it over R and then you see that you get what you imagine as the projective space. If you do it, but you can do it over a finite field also. If you do it over the finite field, so what you see here is exactly the points of the projective plane over FQ. And this is the lines of the projective plane. This is the projective geometry which satisfies between every 2 points there is a unique line. And this is indeed the case, because if you have two spaces of dimension 1, they are contained in a unique subspace of dimension 2. There's a simple linear algebra. So this, the axiom of projective geometry that every 2 points are connected by a unique line. And now, but also you have this non-Euclidean geometry. Every 2 lines intersects in a point. Why? Because what is a line? A line is a 2-dimensional space. If you take two-dimensional spaces in a 3-dimensional space, the intersection of them is always 1-dimensional. So this gives you a model of projective geometry. This is a finite projective geometry. And you get the so-called a point. So what we are getting from this, that S3Q is exactly the so-called the graph of points versus lines of the projective plane. The projective plane over FQ. So that's a very important graph. And okay, maybe we'll take a break now, and after the break, we'll go and we'll study this graph, and we, for example, we'll compute its eigenvalues. And you'll see that we are getting an interesting graph here.